Hi, welcome to my four-part lecture on science and media literacy. In this first part, I'm going to be talking about what is science literacy. To get started, I'm going to ask a number of true-false questions. For each one of these, I want you to think about whether it's true or false. And then after I've read through all of them, I will review the answers. So, true or false? Sea level is rising because the water is expanding. Speaking of the ocean is blue because it reflects the sky. True or false? Speaking of blue, blood in your veins is blue. Speaking of biology, cold weather causes colds. True or false? Now, speaking of getting sick, antibiotics help cure the flu. I've run out of creative ways to link these. Next. We only use 10% of our brains. True or false? Humans evolved from chimpanzees. True or false? Last two. Scientists used to think the Earth is flat. And Einstein flunked high school math. All right, let's go through some of these because some of them are misconceptions. In fact, many of them are. Let's see. Number one, sea level is rising from expansion. True. Thermal expansion is one of the two main factors behind sea level rise. The other is the melting of land-based ice, such as glaciers. The ocean is blue because of the sky. Not true. Okay, sure, if the ocean is reflecting a blue sky, it might look blue because it's reflecting the sky. Okay, sure, but water is actually blue, and the reason for that is when light passes through water, more of the red end of the spectrum is absorbed, and more of the blue light is reflected around. It's diffracted more, and that results in the water having a blue appearance. And this is actually part of the reason why the sky is blue, because the atmosphere contains water molecules, which have these properties with light. Blood in your veins is a dark red. That dark red only looks blue or green because it's filtered through your skin. Cold weather kind of maybe causes colds. So just being cold in and of itself won't make you get sick, but it might depress your immune system. It might stress the body, so you could get sick that way. People in cold climates during colder weather tend to spend more time indoors in close proximity to each other, and so diseases spread more quickly. And some science has even found that certain viruses survive better in cold, dry air. All right, so there is an association between cold weather and illness. It's just not that being cold makes you sick. It's these other things. If you do get sick, if you catch a common cold, you have a rhinovirus. That's what causes the common cold. If you have the flu, and you're being technical about the term, you have influenza, which is also a virus. Antibiotics don't kill rhinovirus or influenza. Antibiotics kill bacteria and some other pathogens, but not viruses. We use pretty much all of our brains. Right now, when you're watching this lecture, certain regions of your brain are going to be more active than others, and so your whole brain isn't active right now. But this isn't the only thing you do. You think about all the activities you do, the sports you play, the knowledge you have, the thoughts you have. All of these things involve your entire brain, if you think about it. Humans did not evolve from chimpanzees. There's what's called a chimpanzee-human last common ancestor. Several million years ago, there was a primate which had offspring that became different, and those groups of offspring later evolved into humans down one evolutionary path and chimpanzees down the other. It wasn't chimpanzees then humans. We evolved kind of together. Scientists didn't used to think the Earth is flat. Scientists have always had some concept of the Earth as being spherical. I think part of this myth is related to the observation or the historic belief about the Earth being the center of the universe, a geocentric view of the cosmos, which some of the ancient philosophers believed in. And of course, that was an inaccurate belief about the Earth. But they never believed the Earth was flat. And Einstein was a math genius. Of course, he didn't flunk high school math. Now, of course, some of these are inconsequential. Yeah, it's nice to have the facts right, but it's not going to hurt anything, is it? Well, it turns out, yeah, it can. There can be problems with holding misconceptions, especially because so many of the decisions we make in this day and age have relevance to science and draw on scientific understanding. So the better we understand science, or the fewer misconceptions we have, the better the decisions we can make. I'm going to give an example about antibiotics. If everybody believes that antibiotics cure everything, then every time anyone's sick, they'll come to expect to get antibiotics. And that makes sense. If antibiotics are the cure-all, we should get them for pretty much everything. If that happens, though, prescribing antibiotics becomes the norm. And over time, due to overprescription and due to patients not taking their full course of antibiotics, things like antibiotic resistance develop. Bacteria become stronger against antibiotics. Antibiotics become less effective. I don't need to explain why medicines becoming less effective is a problem. And in fact, many governments are recognizing this problem and trying to do something about it. For example, here's a video from the Singapore Health Promotion Board.
Look, I can't fight that flu virus. I can knock out bacteria, but not viruses. The flu is not my battle.
And other organizations have taken up the mantle of this cause. So the World Health Organization, which is working on promoting good health throughout the world and developing standards, has come up with its own information campaign to encourage proper antibiotic use. Of course, it's not just the patients who need to be mindful about when and where and how long they use their antibiotics, but also the healthcare providers. For example, the World Health Organization says that if you think a patient might need antibiotics, test to confirm, and then only after testing and confirming, prescribe only when it's really needed. Sometimes people can recover on their own. But there's this issue of overprescribing, and part of the way of addressing that is by addressing this notion of health literacy, helping people understand health information that's out there so that they can make more informed decisions. And that fits under the umbrella of science literacy. This makes sense. People with a good scientific grasp of the world might be able to make more informed health decisions. Now, there's another related literacy I'd like to talk about later in this lecture series called ecological literacy. You can think about this as environmental literacy, understanding nature and how humans impact nature and how ecosystems work. And of course, that has a basis in science. Now, science literacy itself has a basis in some different areas. For starters, knowledge. Knowing the facts of the scientific and natural world, right? That makes sense. If you're going to be scientifically literate, you need to know the facts. But it's also important to understand the process, understand how scientists come to discover new knowledge. What is the scientific method? And given an understanding of that method, people can evaluate science and come to their own conclusions. That's an important part of science literacy. A third component is recognizing the importance of science and technology in society. People who have good science literacy are more equipped to and more motivated to engage in scientific discourse with their friends, families, neighbors, representatives in the government, and they might even engage at a high level in political discussions about scientific issues. Now, I'd like to talk just for a brief moment about knowledge a little more, because knowledge itself is rooted in some other forms of literacy, like basic literacy, knowing how to read and write. Of course, if you know how to read and write, then you can engage with more scientific information, because a lot of scientific information is written down. It's contained in books. But it's not just about reading and writing, it's also about arithmetic. So people who are better with numbers have better science literacy, or at least are better able to understand scientific concepts, and that can be another important portion of their knowledge. So that is kind of in a nutshell what science literacy is. There are certainly more aspects to it, but I think that's a good primer. In the next talk, part 2 of this lecture series, I'll be talking about why having science literacy is important. Thanks for watching.